Does anyone remember what we did on Tuesday?
Nope.
Oh, of course not. We were doing what? Fluid flow, right? And so then we said that fluid flows could be of two different kinds. No, three different kinds. Steady, unsteady, and turbulent. And then we also calculated when does it change from being steady into being turbulent. So now let's talk about other things that are related to fluid flow. And I gave you a thingy, which we called, and that stands for, thank you, viscosity. What is viscosity? Viscosity is the resistance to flow. So think of that as friction that is inherently present between the fluid itself when one tries to flow over the other. So there is a friction that is present between the surface and the fluid, but then there's also viscosity that's present that stops the flow of a fluid internally. So the best way to visualize it is this way. So imagine if I can draw the surfaces like that. And there is water that can flow in here. Imagine this is a layer of water. So the easiest way to think of viscosity is think of this in terms of, instead of thinking of this as individuals, we can think of these as layers of stuff that exist on top of each other. So as fluid flows, think of these parallel plates that have to glide over the other one. So every single one of them has friction in between them. And that friction, I'm just going to call it viscosity. Again, understand, this is not a perfect condition. This is not ideal, but that helps us figure out the math I can have that I can do. So for this case, I'm going to call the area of each of these imaginary plates that develop. It's like equator, right? Does the equator actually exist? No. Like there's not an actual line drawn on the map, right? It's just, yes. And there are no like actually time zones, right, drawn on the map. So if you were to go stand on the equator, there's not a dotted line. It's not like those cartoons. Have you seen those cartoons that have those dotted? That actually doesn't happen, right? So think of this as a visualization tool. And what I'm telling you is imagine if each of these layers has a certain area and it also has to have a certain thickness. So let me call that thickness dy. So now what I am claiming is that if I can divide my fluid into these layers, then I'm claiming that the viscosity acts between the fluid and the plates and also the wall. So the fluid is being contained inside, I don't know, a pipe. If it's an open, it's probably the bank of the river on the outside. It's also the surface that it's being contained in. If it is think of like a water hose. If it's round, it's contained all four sides when the water is flowing. And also between the layers themselves. Good? So that is my claim. So I am claiming, number one, I am going to divide my fluid into layers. And number two, I am claiming that viscosity will act between the plates. And I'm going to say, number three, the speed of each layer will be different. and it will be different by an amount delta V. Small amount, delta V. So now if I was to apply an external force, where do you think it is more likely that the external force will be applied? Probably to the top layer, right? It's easier to make that case. So then how do these plates flow? What will happen is that the top layer will start to flow, which causes the second layer to follow, which causes the third layer to follow behind, and the fourth layer to follow behind, and so on. Do you see the progression happening? I mean, of course, this is not exactly how it goes, but tinier, but this, not drawn to scale, right? Just so, you know, it's not drawn to scale. But that's sort of what you will experience, okay? So that means if I was to apply an external force, the flow would look something like this, where we will still have this as dy. So in general, when the speed varies layer by layer, and there is no difference between the layers, we call it steady flow or laminar flow. If there is, in fact, a difference between the layers, we call it turbulent, right? And in that case, we don't know what to do, and then we panic. We want to make sure that most of our flow stays in the laminar state. And what did we say the condition was for, in terms of speed between laminar and turbulent? Which one is slower? There we go. So once it reaches a critical velocity, then it becomes turbulent. We want to stay below the critical velocity, right? So in that case, I am going to make an assumption and say that my laminar flow is a condition where each layer has the same velocity. Now imagine, like, the velocities of the layers themselves are going to be constant. Good? That means I can predictably say that layer 1 at the top is going with, say, speed 2 meters per second. Not exactly. But layer 2 below that, so imagine if I can say this is layer 1, this is layer 2, this is layer 3, and so on. Will layer 1 be faster than layer 2? And layer 3 will be slower than layer 2. Yes? So that is a condition for a laminar flow. Remember that. Okay? These are assumptions I'm making, which will help me develop formulas for them. Number 4. I am going to try to stay within the steady state condition, laminar flow, and I am going to say where the fluid flow varies from layer to layer, I'm going to call this laminar flow. And in that case, I am going to say that the top layer will be fastest and the bottommost layer will be at rest. And I am going to assume the condition where there is no slippage between the layers. So they're just rolling over each other. They're not sliding over each other, the layers themselves. Again, understand, I'm being very particular because that will help me develop the equation. Okay, in this very general case, I can say F external needed to set up laminar flow experimentally found to be proportional to the area of the plate and proportional to the change in velocity dV that occurs between layers of thickness dy. And understand that that is experimentally found. A lot of what we're going to be doing is experimentally found. So may I write these as F external is proportional to the area of the plate and dV divided by dy. How do I get rid of the proportionality? Put a constant there. Can we think of a constant that would make sense here? Eta, right? So then may I write this as eta A dV over dy? So can people come up with a unit for eta? So what's on this side? Newtons? What's area? Meters squared? What is V? Meters per second? What is dy? A good unit for eta would be Newton seconds over meter squared. And in the time when people were doing this was the 17th, 18th century when people were working on this. And the reason why a lot of people were working on this was because they wanted to figure out blood flow. They were developing catheters. They were trying to have, medicine and how to get blood to people and blood away from people and all of that kind of stuff. And one of the guys who was very involved in this was called Poiseuille. It was Jean-Louis Pascal. How would you say it? He's French. This guy was very involved in this. However, there were no SI units at that time. The units that he used were dynes, seconds over centimeter squared, and he called it Poiseuille? Dynes, yep.
Times the Y?
D-Y-N-E-S. That was a unit for force at his time.